In the previous videos, we've considered situations where there was a gas between the two electrodes. Now, let's consider the situation where all the gas has been removed. The green line on this diagram, for example, might represent a vacuum tube where all of the air has been removed. Now, is it possible to get a spark between the positive and the negative electrodes if we put a high enough voltage difference between them? The answer, of course, is no. It's impossible to create a bolt of lightning or plasma when there's no gas present. In the situation of a vacuum, the only kind of current that might be able to flow between the negative and positive plates would be carried by electrons. So now the question is, if we put a higher voltage on these two plates, can we actually strip electrons off of the negative plate? You might have heard before that a vacuum is an excellent insulator. And while it's true that a vacuum is an excellent thermal insulator, it's actually a good conductor of electricity compared to ordinary air, because once electrons are actually moving through a vacuum, there's nothing for them to collide with that could slow them down. I have the two plates labeled on this diagram, anode and cathode. The cathode refers to the negative plate, and the anode refers to the positive plate. Of course, the ability to strip electrons off the surface of a piece of metal depends on how tightly those electrons are bound to the metal. And this will definitely depend on the type of metal used in the cathode. So you can start imagining the particular situation in this diagram, that in order to get a current to start flowing, the voltage necessary will depend on whether the cathode is made of, say, tin or gold or platinum, for instance. It turns out that it's easier to strip off electrons from tin than it is for gold, and it's easier to strip them off of gold than it is for platinum. The figure of merit used to express this difficulty is called the work function. For example, the work function of tin is 4.4 electron volts, which means that an electron near the surface of a piece of tin would need to acquire 4.4 electron volts of energy in order to make it off the surface of the metal. In gold, more energy would be needed. And this would translate to a higher necessary voltage to get a flow of electrons between the cathode and the anode, as shown on the diagram here. It turns out that it's not very easy to do because all of these energies are actually pretty high. And if the plates are far apart, then the electric field strength would be low, even if the voltage applied is high. One way to make electron emission easier is to heat up the cathode. If the cathode is heated externally, then the thermal energy helps the situation. The current that ultimately flows has a rough dependence on the temperature and work function in this equation. W here is work function. So a larger work function obviously causes the current flowing to be reduced. But a higher temperature causes the current flow to increase. The heat could be applied by using a filament, like in a light bulb. In fact, what I've drawn here is a diode vacuum tube. And this is actually a really useful device. In the early 1900s, this type of vacuum tube was important in the design of radios and power supplies because it does something very important. Notice that by heating up the cathode, it's possible, with a certain voltage, to get a decent amount of current flowing through the vacuum. But the anode is not heated. So if I were to reverse the voltage and instead hypothetically apply a negative voltage to the anode and a positive voltage to the cathode, then it would be much more difficult to get current flowing in the other direction. So this property of allowing current to flow in one direction and blocking it in the other direction is a really useful property. Other than heating up the cathode, it's also possible to supply that energy through light instead. This process is called photoemission. In other words, photons are absorbed by the cathode, which leads to the emission of light. The energy of one photon of light is equivalent to Planck's constant h times the frequency of the light f. so that when a photon is absorbed in the cathode, in order to have conservation of energy, then some of the energy of that photon is used to overcome the work function of the metal, and the rest of the energy of the photon ends up as kinetic energy in the emitted electron. Now, this doesn't necessarily mean that every photon of light shining on a cathode will lead to electron emission, even if the energy of the photon is great enough to overcome the work function of the metal. This is because some light might be reflected. Some of the photons that are absorbed just wind up heating up the cathode. But in order to get any electron emission at all, a necessary condition is that the photon energy must be at least as much as the work function of the particular metal. What this means is that if you do an experiment where you start with monochromatic red light and gradually change the color, going all the way through the spectrum, through green, blue, violet, and into the ultraviolet range, you'll start off with no current flowing at all, and right when the color of the light hits the right wavelength corresponding to the work function, you'll start to see current flowing. In this video, we've considered how electrons might be stripped away from the metal plates in a vacuum, and in previous videos we've considered how electrons might be stripped away from atoms in a gas. Here's a summary of what we've covered so far in the class. So first of all, in the case of static electricity, we found that by rubbing two materials together, we can dislodge electrons from one material and transfer a few of them to another material. That's because one material surface presents a different electric field environment than another material nearby. We've also found that a very large electric field or a very large voltage difference can strip electrons from their orbits in a gas. And this is the situation with lightning or in a neon tube. And finally, in this video, we found that electrons can gain the energy that they need to escape the surface of a piece of metal through absorption of light or heat.